The simple signal call that we've been using so far has a few shortcomings. Early versions didn't automatically restart system calls, leading to the problem I described earlier. Also, the signal was set back to its default behaviour each time, so you had to re-establish the handler every time after the signal had occurred. And the call lacks some flexibility. As a result, we're strongly encouraged these days to use a more complex call, Sigaction. So the first argument to Sigaction is just the signal type. Simple enough. The second argument is where it gets a bit more complicated. This points out to a Sigaction struct. The first field in the structure points out to the handler, or it can be one of these two values, saying to ignore or set the default behaviour for the signal. This is exactly the same as it was for the older signal call. This bit's new, however, because in this second member we can specify a set of signals that we want to block during the execution of the handler. I'll talk about signal sets in a moment. And then there are some flags that you can set to control the operation of the call in a bit more detail. If you want, you can specify a pointer to another Sigaction structure where you will get back the old handler information. If you're not interested in this, just pass a null pointer. Here's a tiny bit more information on the Sigaction structure and the three key members of the structure. The flags value is set by doing a bitwise OR of a number of possible values. I've indicated just 3 of them here. If you include SA reset hand and you exclude SA restart, you will get approximately the behaviour of the old signal call on Unix. Now, what are these signal sets all about? Well, a signal set is basically an array of bits hidden behind a bunch of macros. Each bit represents one signal type. There is a type def for this, it's sigset_t. Usually you will initialize one of these by calling sig_empty_set, which will clear all the bits. You can use sig_add_set to set the bit corresponding to one specified signal. So here we've called it twice to set 2 signals into the set. We can use sig_del_set to remove a signal from the set, and sig_fill_set to set them all. Finally, we can ask the question, is this signal included in the set, by calling sig_isMember, and we'll get back true if it is and false if it isn't. Now, Sigaction isn't as difficult to use as all this detail might be leading you to think. Let's have a look at a little bit of code. Here's our handler, or at least a sketch of it, just the same as it was before. Here we declare our Sigaction struct, and in these 3 lines we're actually filling in the 3 members of that structure. Notice we've asked for automatic restarting of system calls through that flags argument there. And then here's the call that actually does the business. This is where we actually associate the handler with the signal type. Remember that we said that signals are delivered asynchronously. They can occur at any time. But it may be that we don't want to be interrupted in this way. Perhaps we need to ensure that we can complete an update on some critical data structure. If that's the case, we can set the processor's signal mask, which is basically a set of signals that are currently blocked from delivery. Blocked signals will be held pending, and they will be delivered when they're unblocked. But notice that the blocked signals are not queued up. If several signals of the same type are delivered whilst they are blocked, then when they are unblocked, only one will get delivered. We manipulate this process signal mask with the call sigproc_mask. Let's take a look at that. The first argument is basically one of these three integer values. Sig block means we want to add some signals to the mask. Sig unblock means we want to take some away. And then sig set mask says that we want to assign this signal set piecemeal to the process signal mask. This is the sig set t defining the set of signals we want to add or subtract, and we can get the old mask back as well if we want. Let's have a look at a code fragment. The idea here is to set up a region of code that will not be interrupted by a sig hup signal. So we declare a sig set t, we initialize it to be empty, and then we add into it just one signal, the sig hup signal. Then we call sig proc mask, passing in this signal set that's just got one signal set in it, so we're just blocking sig hup signals. So within here we have code that will not be interrupted by a sig hup. The end of that section we call sig proc mask again a second time to unblock that signal. Here's a simple demonstration of Sigaction in action. We have here a minimal signal handler. It just prints out the signal that it received, that's all. In the main program we create a pipe. Now we don't really need a pipe as such. What I do want to get is a descriptor that I can do a blocking read on. In these three lines we're setting up our Sigaction structure. This is essentially the code that I showed you in the slides. And then we call Sigaction to set up the handler for sigint signals. Then we go into an infinite loop. Each time around the loop we do a read on the downstream end of the pipe. Now that read will block because there's no data in the pipe. If the read does return, we print a message to say so, and we print out the value of the error variable errno. So we'll save that and we'll build it. And we'll run it. And it's just sitting there, of course, blocked on that read call. Now if I send a sigint, which I can do very easily by typing Ctrl+C, then we see that the signal handler reports the arrival of the signal, but more interestingly, the read is now returned with an error. It's returned -1, and errno is 4. That's the EINTR value, indicating an interrupted system call. If I do another Ctrl+C, of course, it happens again. Now I can easily kill this program with Ctrl/, which will send a sigquit, which will force termination of the program. So let's go back over to the source code. I'm going to make one small change. I'm going to change that 0 in the flags to be SA restart, which will make the system automatically restart those system calls. So we'll save it, build it again, run it again. And this time if I press Ctrl+C, well, the signal handler reports the arrival of the signal. Do it one more time there. But you'll notice that the read is now not returning. This is because it's being restarted automatically.